Hi folks, Aaron Harper here again. Gotten a little bit of a complaint that folks couldn't see the numbers on the last video that I did with all the math for the figuring out the distance. So I won't be doing a whole lot of math on this. I'll basically be posting the equation in a much larger format, but we won't be able to step through it line by line. Fortunately, this is logarithms, so it's simply a matter of just plugging it into your calculator and going for it. What I will do is later on, with better equipment, I'll be redoing these videos to yield a better result, and probably put a lot of the graphics that I normally put on here. I'll be putting those on sort of a computer generated format so that it can be read more easily. All right, this time, oh, and one other thing. If you hear things like with the wind whistling, this is actually indeed what you are hearing. Winds are gusting at 60 miles an hour, and they have found a little gap in my lab here that makes a whistle. So bear with me. This particular one is taking the data that we got from the previous thing, where we were looking for what they call the slant distance, or distance to target, from the observer on Earth to ISS as it flies overhead at 60-degree elevation, and that yielded 400. Let's see, what was it? 457.42 kilometers. The question is, how does that affect the radio signal? Well, you know the expression, there's an app for that. There's an equation for that. So without further ado, I'm going to go ahead and post the equation in all its glory, and we'll walk through it a little bit. First thing is, for propagation loss, the actual full equation is 4 pi df over c. Now, this does not yield decibels. This is not the same format. In order to get that, you need to take this whole thing and put it into a natural logarithm. But the functions are, you have 4 times pi, which is fairly self-explanatory. D is your distance, and F is your frequency. And all of this is over the speed of light. The reason that the speed of light is involved is because of wavelength. Frequency over the speed of light is, or rather, excuse me, lambda is the measurement of the radio frequency's wavelength. What this means is more is due to the length of the radio wave as it goes up and down, and the distance from point A to point B as it crosses the zero line, or from peak to peak. It's essentially the same thing. But more has to do with the wavelength than actually the frequency, or how many times per second it does anything. In fact, the geometries of radio equipment is based not on frequency, but rather lambda. So if you take the frequency of something as it's traveling the speed of light, speed being distance over time, you get a function of frequency over the speed of light. Now, like I said, this is not the logarithmic function we're looking for, but this is the basic equation. As you can tell, there's also a couple constants in here, 4 times pi. What's interesting is, if you adjust a few things and tweak a few numbers, you end up with a whole different set of units, which you're basically restating the exact same equation, just in a way that you can use right out of the box. And I'm going to go ahead and restate the equation in a way that can be directly used, where the numbers yield, it's expecting the frequency in megahertz, which is what we need, and it is expecting the distance in kilometers, which is precisely what we need. So, without further ado, it is 20 log 10 d, where d is the distance that we developed in kilometers, the distance to the target, plus 20 log 10 and the frequency measured again in megahertz, plus the standard figure of 32.45. So 32.45. And this gives us our free space propagation loss in decibels that we can actually use. The result is that in our use, where the distance was 400 and whatever, let's see, 457.42 kilometers, and our frequency is 145 megahertz. The result is that our actual free space propagation loss is 128.7366. Negative 128.873666 dB. Yeah, that's a big figure. Like I said in the last video, this is the reason that it's challenging. There's a lot of distances involved and so on. The thing you may notice is that frequency is involved in the calculation, though. You might ask if it's distance related completely, why is frequency a factor? Well, there are two reasons for that. The first is the results of the inverse square law as it spreads out the energy. Remember I said that lower frequencies behave more like sound, while higher frequencies behave more like light. Well, the inverse square law does not apply universally to all frequencies. There is a difference between how the frequencies react. The second effect, and this is the important one, is the results from the antenna aperture change. This affects the way the antenna can pick up the signals, and this term is frequency dependent. What it means is there is a stronger, a much greater difference as frequency goes up in things like mismatch, in things such as the distance between objects and so on. So therefore, a higher frequency will have a higher attenuation in this way. But minus 128 dB is not bad. The thing you have to bear in mind, however, is what comes from the next step is what's important, because that determines what we receive. Now, the interesting part about this is if we go back to our previous work, where we were putting out 78.5 watts, we have 18.95 dB. Well, now, we can take that away from there. So We started out with 18.95. You know what? Let's not even worry about those smaller figures. Let's just truncate it at 2 decimal places and be done with it. Well, what do we have? If we take 18.95 and subtract 128.87, this becomes, carry the 1, there's 15, becomes 8, 0, 0, ooh, look at this. We have a problem. It's less, but that's okay. Because what we end up with is we're down to negative, minus 110.08 dB. That's still a substantial amount to recover, but it's not impossible. The big thing to remember here is receiver sensitivities often go into the 80, 90, sometimes into the 100 dB range. So we're almost there. And now if you just mentally add, let's say, a 6 to 12 dB antenna, you are so close. So close. So now if you add a 30 dB preamp to the whole mess, now you've got it. Because minus 110, let's say your receive sensitivity is 90 dB, it means you've got 20 dB to make up. If your antenna gain is 6 dB, you're down to 14 dB left to gain on this. Now, if you add a 30 dB preamp, you're at the positive 16 dB. And in the case of most digital encoding, it works just fine at 12 dB worth of signal. Now, the one thing to bear in mind here, though, is that doesn't take into account the noise floor. And we'll cover all that next time when we do the transmission segment. But this we can do. Till next time.